My name is Fabrizio Mo. As you probably remember, I'm the Vice Chair of the IEEE Student Branch. I'm very glad to be here at this Tech Talk. That's a pleasure for us to host here at Politecnico di Torino. And as you probably know, the event will be recorded and uploaded on our YouTube channel. So if you want, you can follow us on YouTube and our social networks. At the moment, we have something like 20,000 visualizations, so we are growing, and this is more or less the situation. I would like to start with a brief introduction by Professor Maurizio Martina, and then with the tech talk. Thank you.
Okay, thank you, everybody. And I'm very glad to have you here this evening, and I'm really glad to have people from Synopsys. Probably you know Synopsys. One thing, as you know, old people are always telling boring stories, and you know, I'm old right now, so I'm going to bore you with a boring story. But one thing that it's my real experience is that when I started working on my thesis in 1999, the first instrument that I was using for simulating the VHDL that I developed for my thesis was the simulator by Synopsys. So it's a great pleasure for me after, I'm not telling you the number of years, but many years, having here someone representing Synopsys for telling us something about Synopsys. And then during my work, I had the possibility to know a lot of tools related to Synopsys, mainly design compiler, but also other tools. But the interesting thing, and I think that the people from Synopsys today are here mainly for telling you that, is that Synopsys is not only developing tools for integrated circuit design, but also something else. And this something else is, at least in my opinion, very interesting. So I'm not going to bore you any longer, and I will leave the stage to Matteo from Synopsys.
Okay. I try to avoid the mic because we are people, and I usually have a good voice to talk without the mic. So thank you for the introduction, and I'm happy to be here. This is the first time I'm in the Politecnico Torino, so nice for me. I'm going to talk about Synopsys. First of all, a brief introduction to the company and to the team, and then I will let Darjn go ahead with something more technical. So hopefully I'm not going to bore you as well, even if I'm probably as old as Professor Martina, so maybe I have to look from this on this side. Okay, so introduction to Synopsys. Synopsys is an ADA company that is not only doing ADA, because Synopsys has the broadest IP portfolio in the semiconductor. So this is a slide showing some numbers, number of employees, revenue, number of patents, number of. Here is just to tell you that the company is doing good. In the last 10 years, the revenue are growing, and that and it's a worldwide company, as you can see from the map. Synopsys is doing almost everything that is related to integrated circuits. From software, and from silicon to software. So is doing everything related to circuit simulations, analog and digital, verification, software, and also is providing IP. What is IP? I will talk about it in a minute. This is the verification platform. Verification is an aspect of the design related to the digital design. The digital is very complex, digital design. You end up with millions of gates, and you need to be sure that what you have designed is what you want to design. And on the analog side is simpler, the verification, even though you need to look at the femtosecond. On the digital is another dimension, other issues. And so verification requires a lot of computation and a lot of tools. This is the digital design platform. I'm not going to talk about the details. And this is the analog design platform, including analog layout. This is the IP portfolio. Different kind of IPs. SiC, processors, digital IPs, physical IPs. Physical IPs means that is something that is complete. We give to the customers the layout, the design and the layout. Digital IPs, we provide only the netlist and what is required to the customer to implement their systems. Processors, you know what processor is. This is a nice slide that is showing the, let me go, okay. These are the process nodes with the colors. The light color, let's look at this for example. The light color is showing the number of tape outs at a certain quarter done in the specific process node. And the dark bar is the number of tape outs done using the Synopsys PNR flow. So this is just to show that in the recent process nodes, we are talking about 7, 5, 3 nanometers, almost 80–85% of the tape outs in the world are done using the Synopsys PNR flow. Let's go to the IP, because we are here to talk about IP. This is the distribution of the sites in the world. I would like to highlight that there are more than 3,000 employees in Europe, just in the IP design part of the company, distributed in 17 countries. And as another message that I think is important to pass, during last year, 2021, the number of employees hired by Synopsys in Europe is higher than the number of employees hired in Asia. This is the first time that it happens in the last probably 20 years. So it's a message that is important. So let's go quickly to Pavia. What are we doing in Pavia? In Pavia, we are designing SerDes serial interfaces. SerDes is a serializer and deserializer. Is a specific IP to manage the interfaces between a digital core and a cable. Okay? Every time you go in and out from a chip with a lot of data, and I will show you the applications of this kind of design, you need a SerDes, and you need a high-speed SerDes because you want to decrease the number of wires. So we are talking about 112 gigabit per second, in a plan for plan for coding. And the mission is to create a team with all the functions required to design this kind of chip. So analog design and layout, digital design and verification, firmware, system architect, application means hardware measurements in the lab. We are also exploring the silicon photonics side of the design with some new investment done by the company. And we are talking with, we are in Italy because in Italy there are these kind of competencies, and we are talking with the universities, not only University of Pavia, we are here to talk about, because in Italy we have the capability to do this kind of activity, but we need obviously to attract the good talents that are in the university. We are already one master thesis student in the company, and we have programs to have 2 PhDs, hopefully starting during 2020. The team established in last year, almost 1 year ago, and the office that we have opened 3 months ago. During this year, less than 1 year, we are now 23 people, and 6 of them are women, which is not so easy to find in our world. And the plan, long term, but is not so long, is to reach 50 people. And we have many positions available on all the figure that I mentioned before. This is something that I think is really important. We are here because we are looking for junior engineers who like challenges, because it's not easy to design a SerDes, but it's very interesting. I'm designing SerDes for 20 years now, and every day I have something to learn. Every day I have an interesting challenge in front of me, and it's really a good job, because you never got boring, like Maurizio was saying before. You will find a real team. What does it mean? We are not working on individual tasks. We are working as a team. We are helping each other. We are helping junior people to understand what they have to do and to learn this job. And so, every day we have to invent something. So it's an interesting job. Let me give you a very quick story from the time, a very quick introduction to the SerDes. Where are our design used? This is the biggest market, data center. What is a data center? Data center is a building like the university, like the Politecnico, where you have only this kind of equipment, all switches and big devices, and where data are coming in, like you have to think to Amazon, Google, Facebook, this kind of companies are customer for these IPs, because every time you have a data stream that is entering in a chip, and will be managed by these devices and have to exit from these devices, you need a service. Optic connection is something that is becoming familiar. We have the fiber optics that are entering our home now. It was not like this 10 years ago. Artificial intelligence is another field because a lot of data need to be managed by these big chips. And then everything, telecom, industrial, medical, digital home, you have the Wi-Fi router, automotive, now even more and more the cars are equipped by microelectronics, and every time you have something, you have data that need to travel. IoT, storage, graphics, gaming. These are the applications where you need to move data. Where you need to move data, you need a service. This is the traffic in the last 5-6 years. Exabyte per month. This is the bandwidth of the mobile devices. More traffic, more bandwidth. Again, this picture of the data center. This means we need service and we need high speed and even higher speed. Increase speed and reduce power. Why reduce power is important? So increase speed because you have a lot of cables. If you increase the speed, you can remove the cables because the same cable can manage more data if you increase the speed. Power, because this is the data center again, and the more, have you ever tried to work with your laptop on the sofa? How, during summer, what is happening? Your legs get hot, okay? Because electrical devices means temperature. The lower the power, the lower the temperature that you produce. The big problem here is how to reduce the temperature of these rooms. You spend 50% of the power to move the data and 50% of the power to decrease the temperature of the rooms. Because if the temperature goes too high, your devices are no longer working. What is happening if the Facebook connection has an interrupt? You see it on the newspaper, because this should never happen. Okay, so temperature is an issue. Literature, 20 years. 2000 to 3 gigabit per second. 2020, 60, 65 gigabit per second. Now we are at 100. Okay? So in 20 years, the speed has increased by a factor of 20, 30. Okay? Power efficiency, the same publications. Power efficiency. In 20 years, the power is decreasing, not only because of the technology scaling, but in particular because of the architecture changes, design improvement, and because the work that we do, not only, also because of the technology, because the technology is helping, but you need to invent we need to invent new architecture, a new way to do the same function with higher bandwidth and lower power. What is a service? Is a transmitter and a receiver. In the middle, you have the channel. The channel is a board, or a cable, or a fiber channel, or a trace in the package. Whatever, not wireless, not air, but whatever is a physical connection is a channel. You have a lot of non-idealities, and the channel loss means that the bandwidth is not infinite. You are losing signal. Electrical noise, timing jitter, power supply noise, a lot of non-idealities. We move from NRZ, which is this kind of way to transmit the signal, to PAM4. Do you know how much is this time interval at 100 gigabit? 18 picosecond, 1/8 picosecond. It's really interesting. I'm done. Darjn, you can go ahead with some more technical and digital description. And then if you guys have some questions, we are here even after the talk. We will be happy to answer.
Hello to everyone. I'm Darjn Esposito, and I'm a digital designer in Synopsys. And in this talk we will discuss about an introduction to DSP-based SerDes. This is the agenda for today. We will give a brief overview of the digital system. We will discuss why we need to equalize, and we will focus on two main DSP blocks of our SerDes system, that is the feed-forward equalizer, and the decision feedback equalizer, the DFE. Then we will introduce some challenges related to the modeling and verification that we have in our system. Okay. Here on the right side we have the ISO OSI abstraction layer models. Okay. Here we have the higher layer that have the bigger abstraction. Okay. And our integrated circuit, our work is easier in the physical layer. Okay. And in particular, this is what we do in Synopsys Pavia. We make the design of the PMA, okay, that contains the DSP and the analog circuitry, but also a part of this layer that is the PCS, physical coding sublayer, and the half part of this layer with the PMA makes the PMD, that is what we do in our design center. This circuit makes power-up sequences, RX and X detection, calibration to assist the digital circuits, and so on. Here we show our IP. This, okay. On the left-hand side we have the SoC, okay. On the right-hand side we have the external interface, we mean the channel. So we have signals that are arriving so our received signal, and signal that we have to send from the SoC floats outside. This is the transmitter band. Okay. You can see here that this is our IP, that is the PME. Okay. And inside the PME we have the PME. You can see that the PME is composed by multiple lanes. What is a lane? Is a combination of a transmitter and of a receiver. Here you can see that there are some green parts. Green parts means analog, so this is obviously our mixed signal circuitries. The blue part is digital, the green part is analog. Obviously the part that has to interface with the channel is analog. We have some circuitry to, we have a PLL, okay, with some digital circuitry to manage, okay, the PLL. And outside we have a microcontroller where we can run firmware. The firmware is very helpful for us because it gives us flexibility to change algorithms. For example, the algorithm to make the calibration to assist the analog circuitry, to change the power-up sequences, because obviously there is an analog circuits that requires some specific sequence, okay, to power up and power down. You can see there are some DFT features, some interfaces. There are obviously a register map and clock management, finished state machine, and so on. Okay, we have introduced so that a lane is composed by a transmitter and a receiver. Now we will focus on what is inside a transmitter and what is inside a receiver. Obviously, a very high-level overview. A transmitter. So, what is the task of the transmitter? Is to take a parallel data, okay, and to serialize it. We can see that we have the front end that is digital, and the final part is analog. Inside what we have, from a digital point of view, we have our functional data. Here we have a PRBS generator that is an LFSR that is used to debug, let's say. And we have an FIR filter that is used to pre-distort the signal before to make it traveling over the channel. We have finished state machine to calibrate, to assist the analog circuitries. And then we have this part that is mixed. We mean that we are passing from the digital to the analog interface, and we have a digital to analog converter and a driver to give power to send the signal over the channel. You can see that we conceptually have to serialize data. This means that we must keep the same data rate between this here and here, but going from a parallel data to a serial data. We mean that here we are increasing, specifically in this part, we are increasing the clock. We mean that this, in particular, this interface is very critical from a digital point of view in terms of timing. Obviously, we always have the challenges to decrease the power and to keep the area. After the channel, we have the receiver. The receiver is making the opposite task. It's taking the serial data, and its task is to convert the serial into parallel data. Here, obviously, the situation is reversed. We have an analog front end because the data is analog. It's traveling over a channel that is a low pass behavior. So we have an analog front end that makes some equalization. We have an ADC, and we go into the DSP world, where we have an FFE that is a feed-forward equalizer, but it's conceptually is an FIR filter. We have a decision feedback equalizer. We have some calibration finite state machine, an adaptive filter. What is the task of this adaptive filter is to control, for example, the coefficients of the FFE, the setting of this block, the coefficients of DFE, and so on, and to control also the blocks into the transmitter, to have a bit error rate near to 0. Okay, so this makes an adaptation that is obviously a function of the channel and of the data rate. We have a PRBS checker that is checking that what we are sending for the bug from the transmitter is what we are receiving. Okay, what is the challenge? What are the challenges here from a digital point of view? Timing closure as usual, in particular in the DFE, that is this block that we will discuss later. Obviously, the power efficiency and the area. Now, why we need to equalize? Let us assume in a very simplistic view our system that is a transmitter, we have a channel and a receiver. And what we send is a signal like this. For example, this is a non-returning 0. You see that we have only 2 levels, 0 and 1. Currently, for E1 112 Gbps, we have a signal that has 4 levels. Okay, and an usual tool that is used in SerDes to qualify the quality of a link is the IA diagram. The IA diagram shows all the possible transitions, okay, that this signal can do. So can do 101, 010, 111, and so on. Obviously, if we have to sample this signal, we have to sample this signal in the middle. So we must be far from the edge in order to not have a metastability issue. This is what we receive when we look at the end of the channel. We see that this signal has no information, let's say, because we don't have this high, okay, this high amplitude. And the task of the equalization is to have something after the channel that is like this. Okay, why we have this kind of behavior? Because we are sending, let's say, a digital signal, but the channel has a bandwidth, is a low pass filter, and what is happening? It's happening that over the channel we are sending these current paths, but we are sending future and past samples. So if we take as a reference this a specific path that is our cursor, what we receive is this. This is the ISI, inter-symbol interference, this contribution, okay, that are due to the fact that the channel has a low pass bandwidth and that are traveling the past and the future signal over the channel. So the tails of this pass, okay, make this interference. Okay, this contribution of ISI related to the past samples, past signals, are clearly post-cursor. This part that is the future is called precursor. So the task of the equalization, the target, is to bring to 0 the precursor and post-cursor ISI. This means that we have an I as this. Okay. Now the channel is is a low pass filter. Okay. Can be discretized using, for example, techniques like the bilinear transform in order to make an FIR channel of the filter. Okay. And therefore we can use obviously in an approximated way another FIR filter that is called in RX FFE to invert the channel response. So this filter must have a high pass behavior, okay, and can compensate the ISI due to both the precursor and postcursor. You can see that here, if we insert in our FIR a latency, okay, we can take into account the precursor, the cursor, and the postcursor. We mean the current samples, the past, and the future. For example, we can use some constraint on the maximum gain on the filter, and we can select, for example, the signs in order to have a high pass behavior. For example, here we are making the maximum gain happening at 90s frequency. Since we have to meet a high data rate, okay, for example, in 112 Gbps, okay, we have to go over a parallel implementation in order to keep the clock frequency low. For example, 112 Gbps, we can have 56 ADC, okay, running up to 1 GHz, okay. So we have multiple FFE, okay, for example, 56, each one that can have a certain number of coefficients of taps higher than 10. You can see that we can have more than 500 multipliers inside our FFE. This means that this block is the most power-hungry block of our system. It's dissipated about 30–40%. Okay, obviously this contribution is going to improve when we have newer techniques, but we always have to think how to decrease the power, obviously the area, how to close the timing. So we have to use pipelining and so on. What are the design solutions? Obviously, we have to try to reduce the voltage. This is, for example, what happens if we decrease the voltage. Here we have the energy expressed in terms of picojoule per bit. You can see that we can drastically, obviously, decrease the power of our FFE. We have to think how to optimize the multipliers, for example, using CSD representation and so on. And in general, the bit width of the coefficients are not equal. We mean that since, for example, here you can see that the ISI of the post and of the precursor that are far from the main cursor is lower. Okay, this means that we can use taps that are a reduced range, a reduced bit width to compensate the cursor that are far from the main one. After you can see here that after the FFE we have the DFE. The DFE is the last block of the RX data path, and it takes the final decision. We mean that here we have, you can see a quantizer, a slicer that says, okay, we are in PAM4, we can have, for example, +3 or -3 symbols. That is the symbol that we are sending if we are not doing any error. Or if we have 4 level, we have this kind of choice, okay, in terms of receiving signal. So this is the output of our FFE, okay, and you can see that this is a nonlinear equalizer because there is this quantization, okay, but there is also feedback. What is doing this feedback? Here we are trying to mimic the channel response. So this is an FIR filter that is trying to mimic the channel behavior. And let us assume that we are not doing any error. We mean that the signal that we are detecting here, for example, we were sending a 3 with at our transmitter, and we are receiving a 3. So here it is like if we are at the end of our transmitter, after our transmitter we have a channel, we are trying to mimic what is happening at the channel in order to have the same ISI contribution that we can subtract from our incoming signal. And this is how the DFE works. What is the effect? The effect is, if you consider the blue curve, okay, this is, for example, the post-cursor 1 and post-cursor 2 ISI. If we use a DFE, we can mathematically remove the ISI, that means bring to 0 the ISI, the interference due to the post-cursor. What is the drawback? A drawback of the DFE, one of the drawbacks of the DFE is that in order to respect the causality, it can only compensate the past, the post-cursor, not this part that is the precursor. For this we have to use, for example, the FFE. An advantage over the FFE of the DFE, it is that because it is nonlinear, it does not amplify the noise in the high part of the bandwidth, as opposed to the FFE. this is for example, what we have without the DFE. This is what we can have. You can see we have an eye with a certain amplitude. Okay, if we use the DFE equalization. We can consider, for example, only a tap, only one tap that is, for example, post 1, okay, and we can obviously implement this multiplier with this multiplexer, because here we can have +1 -1 times our coefficient. This means that we can avoid a multiplier and implement this as a multiplexer. Since we have to maintain high data rate, also this circuit cannot be implemented, let's say, serially, because we would need a clock frequency in the order of the tens of gigahertz. So we have a parallel implementation with a certain number of slices that can match the one used in the FFE that can match the number of ADC. And okay, this is what we have. We have that this is the one of the input of the output, of the FFE. We equalize this taking as input the previous sample that in our case is the previous decision of the previous word clock cycle. For the second one, we take as decision the decision of the previous slice in our same clock cycles, and so on. What is the issue of this topology is the critical path, because you can see that critical path here in red starts from here and goes for a multiplexer, adder, slicer, and so on. So this is our critical path, clock to Q plus n times the delay of the max, of the adder, and of the slicer. This is obviously an issue if we have, for example, 56 slices, because we have 56 ADC, for example. So we need to reduce this critical path, but unfortunately this is a circuit that has a feedback, so cannot be pipelined. So what we can do to close the timing? We can do the local rolling. We mean that starting from this situation, okay, we can do some pre-computation. For example, we, at the expense of the area, obviously, we evaluate both the input plus our tap, both the inputs minus our tap, we have the slicer, and just after this, we have our multiplexer that selects the correct computation as function of our previous symbol detection. What is the advantage of this is that we are removing, okay, the timing of the adder and of the slicer from the feedback. This part, we still have this timing, but this part becomes feed-forward, so it can be pipelined. Okay. If we use this technique in our previous example, we have this circuit. If we check the critical path of the feedback part, okay, we have that now we have removed, as you can see, the delay of the adder and of the slicer, and we have only the delay of the max. Is it okay, for example, for the state-of-art implementation? Not yet, because we can have a number of slices that is higher than 30, okay, and we also have a band form modulation. This means that this is not a 2-to-1 multiplexer, but is a 4-to-1 multiplexer. So we need additional solutions. An additional solution is to use a look-ahead multiplexer. Okay, obviously we can describe a multiplexer, okay, if this is our hypothesis A and B, okay, this is our max, okay, a multiplexer can be expressed in this way, obviously. So we have that our output is A if our previous symbol is 0, otherwise is B. If we consider what is happening at our previous iteration and we substitute this one into this, we obtain this expression. In this expression, we have two levels of multiplexer. One that is this, okay? So we are selecting A or B as function of our previous A hypothesis. And this one is doing the same, but with the selection of the max, that is the B. And after this, we have a second level of max, okay, that is taking this one as a function not of our previous symbol, but of our two previous symbols. Okay, what is the advantage of doing this? If we consider our previous example, now, for example, the first slice is not taking our previous symbol of the previous clock cycle, but of two previous symbols. Which means that we have this kind of connection. Here is not taking the previous symbol, but two previous symbols. So, is this. This means that we are halving the critical path, because now the critical path of the feedback part is traversing only two multiplexers. Okay. So, with this look ahead technique, in general, the critical path is divided with this factor. For example, we have 56 slices. This is our look ahead factor that is equal to 2 in our previous example. We can drastically reduce the critical path, but obviously at expense of the max area. Okay. For example, okay, if we have a number of DFE taps that is higher than 1, and if we keep the look ahead factor at minimum to sustain the desired data rate, okay, we have that our max area increases exponentially. You can see here the number of taps. Let us focus on this red curve that is a 14 nanometer technology. Here we have the MUX count. With one tap we have we are just lower than 2000 max. Okay, if we use 2 taps, 2 DFE taps, we have 10,000 multiplexer. Okay, if you use 3 taps, okay, we have let's say probably 50,000 multiplexer. So you can understand from here that it's true that the DFE can exactly equalize, okay, the post, okay, but this is happening at the expense of complexity, of PPA performances. So this means that the task of equalization must be, okay, shared between the DFE, the FFE, the analog blocks, the transmitter equalizer blocks, and so on. This is a final slide showing that okay, our system is very complex, and obviously we need to model it. Okay, how we model it? For example, we have to model the analog circuitry to run our digital simulation, because the system is very close, okay, to the analog behavior. We have an analog to digital interface, for example, into the receiver. We need to make simulation, accounting also for the digital, for the analog parts of it. So we model this with system variable using real number modeling, but we also have to model our DSP. Okay, so we have reference model done, for example, in C++ to make simulation between the digital and our reference model expressed, for example, described, for example, in C++. And this modeling so is used to verify the system, to verify using block level tests. These tests are done by the RTL designer, okay, that can use these models to run the tests, to test the arrays, the TICs, the PMD, the CM, that is the block that manage the PLL. But also we have verification engineers, okay, that make a coverage-driven methodology, okay, so using this model to run simulation coverage-driven for the subsystem, so for the TICs, RX, the lane, simulation to validate the firmware, okay, so hardware-software co-simulation, and to validate the register maps. That's all.